All right. As people are clicking over to come into this session, welcome. Good to have everybody here for our very last session of the day. Hope everybody's had a great day so far. Our last session for today is Moving Out, Technologies for Sustainable Exploration. From long duration deep space missions to permanent sustainable habitation on the lunar surface, this panel will look into what capabilities are necessary to take humans farther into the solar system than ever before and stay there, and how these technologies can support innovations in their earthbound counterparts. Thank you to our sponsors for this session, Aerojet Rocketdyne, Blue Origin, and Northrop Grumman. We appreciate it. Our moderator for this panel is Jim Ryder, Associate Administrator at NASA's Space Technology Mission Directorate. Jim, always good to see you again, and it's a shame we couldn't get another administrator in there with our name, but you know, we do what we can.
Yeah, it's good to be back, Jim. It's always a pleasure to join you in these sessions. I always learn a lot, and it's great feedback. Thanks.
Take it away. Thanks.
All right, thank you. Well, you know, I'm really interested in this subject because really sustainable exploration is what we're trying to do with the Artemis program and as we go in the future, and also while supporting economic development here on Earth. That's really a key topic right now. So what I really like about this panel is we have 4 panelists from industry, each have a broad perspective on the subject, and we'll be coming at it from a different viewpoint. And so I'm really looking forward to hearing what they have to say. So I'd like to introduce the 4 panelists and then let them give a few opening remarks. Kerry Timmons is Lockheed Martin's Systems Engineering Design and Integration Senior Manager for the Orion program. She leads a team of engineers working requirements and verification, mechanical and electrical integration, and human systems integration for the Artemis 1 and 2 missions that will support deep space exploration missions to the moon. Next then is Kate Kelly. Kate is the Advanced Nuclear Systems Program Manager for Bwxt Advanced Technologies, leading nuclear development projects to advance the company's R&D interests in advanced manufacturing and nuclear thermal propulsion technologies. Then Joe Anderson. Joe is Vice President of Operations and Business Development for Space Logistics LLC, which is a wholly owned subsidiary of Northrop Grumman. Joe is responsible for managing the technical, operational, licensing, and insurance aspects of space logistics satellite servicing fleet, as well as business development for commercial and government satellite servicing. And then finally, Elliot Carroll. Elliot is co-founder and CEO of Lunar Resources Incorporated, a space industrial company pioneering in space manufacturing and space mining technologies. Elliot oversees the strategic direction and the operational management for the company, focusing on developing an in-situ manufacturing architecture for the cislunar domain. So we've got people talking crew systems, nuclear systems, satellite servicing, and in-situ manufacturing. And so with that, Kerry, why don't you start and give us a little bit of introduction.
Thanks, Jim. I'm not sure, are folks seeing my charts or available? Okay.
Now we do.
Perfect, thank you. I am very excited to be here this afternoon to talk about Orion and the technologies on this spacecraft for sustainable exploration. So next slide. I wanted to give an overview of our spacecraft and orient folks with what I'll be talking about today. Starting in the center of the slide is our crew module. This is the capsule that will carry 4 crew members through ascent on their mission and return them safely to Earth. This is where we keep the advanced avionics as well as the environmental control and life support systems we need to keep the crew healthy and active. Moving to the left is the service module, which consists of both the European service module as well as the crew module adapter. Here's where we keep our powerful propulsion systems as well as the crew consumables such as water and the breathable oxygen. Then you see some components that allow us to interface to the launch vehicle. And on the right is the launch abort system, which can be activated in milliseconds to take the crew to safety in any anomalous situation. So that's the overview of the spacecraft. And if you go to the next slide, I'll talk a little bit about some of our key technologies. That upper left-hand picture is the Orion spacecraft at Bwxt Station as we were completing our environmental qualification testing. And this picture really shows to me that it is a closed system. We're not going to be able to stop and pick up resources on our way to the moon. So the systems such as the environmental control and life support system have to be able to reuse and regenerate those supplies on board. In particular, we have one component that's a phase change material heat exchanger that can accommodate high thermal loads, such as when the crew is exercising, which is important to crew health during these long duration missions. Moving to the right there, I've got some pictures of the radiation vests, which are actually designed and built by an Israeli company. And they're attached to torsos developed by a German company. So really an international endeavor here on the Orion program. But deep space environment is so different than a LEO environment and much more dangerous from a radiation perspective to the crew. So what we're doing is developing technologies on the Orion program to help characterize and protect the crew in those environments. And then there in the bottom left is our heat shield. You see a bunch of AVCoat blocks, which are really the same materials used on the Apollo program. But some of the technology advancements here are really in the manufacturing and how we make those, which make them more affordable and more reliable in that build process. That heat shield can protect the crew from both re-entry speeds for the moon and from Mars, when we'll see temperatures near 5,000 degrees Fahrenheit. And the last thing I wanted to touch on was our communication and navigation systems. That picture in the bottom right is of the S-band phased array antennas, which can communicate long distances when the Orion spacecraft is as far away as the moon or farther. And what's not shown here is other advanced technologies, including a transponder, which does range and range rate data for rendezvous and proximity operations, for docking, and a baseband processor, which does encryption and decryption, key technologies to make sure the data that we are sending and receiving from the vehicle is pure and intended. So those are some of the key technologies for Orion. And if you go to the next slide, we have been developing those technologies and testing them in labs, but it'll be Orion at the gateway and beyond that, really demonstrating these on missions where the crew is using these and the Mission Control Center is exercising all aspects of the vehicle to understand and keep the crew safe in these events. When we're in LEO, we can get home in a few hours. At the moon, it takes a few days. And then my last slide is a picture of Lockheed Martin concept for a Mars lander. All of these technologies are building blocks that will feed into future missions, whether it be at the moon, Mars, or beyond. So there you go. Thanks, Jim.
All right, thanks, Kerry. That's quite a lot of technology in while it's large, it's a small package to fit everything in. That's really exciting. Next, we'll go to Kate.
Hi, good afternoon, everyone. As Jim said, my name is Kate Kelly. I'm currently a program manager with Bwxt. I've been in the nuclear industry for a decade and Bwxt for almost all of that time. And it was really the number of interesting opportunities in development and manufacturing that drew me to the industry and have kept me with Bwxt. And I'm really excited to talk to you all today about some of those projects and the technologies that are enabling space exploration and clean energy. So on the next slide, I'm going to start by giving some background on Bwxt. So we are a nuclear technology and manufacturing company headquartered in Lynchburg, Virginia. For more than 60 years, we've been developing and delivering nuclear reactors for the government and commercial applications, beginning with the USS Nautilus, which was the first nuclear-powered submarine. That support has continued through generations of designs for commercial and space applications. Our legacy includes numerous space nuclear programs over the past several decades, including most recently the conceptual design and fabrication development support for NASA's Space Nuclear Propulsion Program, which we've been working on since 2017. So on to the next slide. So how does this relate to sustainable exploration? So nuclear power is environmentally friendly. It has fewer greenhouse gas emissions than traditional sources. It enables a reduced reliance on fossil fuels and has a higher power output compared to other renewable sources. But there's cost, schedule, and regulatory reasons and restrictions that have limited the growth of commercial nuclear power over the past several years. There's a few things that we're working to do to help address this. There's programs that BWXT is participating in, like the Department of Energy's Advanced Reactor Demonstration Program, which is shown at the bottom left-hand corner of this slide. These programs are trying to advance technologies that can improve the economics of nuclear and address some of those cost reasons that are preventing commercialization to date. In addition, there's the ongoing opportunity to use the broad interest in the government, particularly for space applications, to help advance these nuclear technologies. And a few of these programs are highlighted on the slide that you see here. In all of these cases, we're using uranium as our fuel source, and a fission chain reaction of a uranium isotope is going to produce the heat that generates power. The reactor and the supporting systems around that are then tailored to produce the amount of energy we need and survive the conditions that are specific to each of these applications. The large amount of energy generated through this fuel can enable a performance benefit over other sources, which provide access to remote places in space and on Earth. One of these applications is to use nuclear as an in-space power source for sustained presence on lunar and planetary surface. Another uses nuclear thermal propulsion, which is an approach supporting the objective of pushing human exploration from the moon and further onto Mars. This enables a performance benefit over chemical propulsion and leads to or allows for shorter overall mission times and less exposure to cosmic radiation for the crew. Also, there's government programs that are developing nuclear power sources for remote or off-grid energy for terrestrial applications. So this is being explored on the DOE's ARDP program that I mentioned earlier, and is a capability of interest to DoD, for which BWXT Advanced Technologies is performing final design activities of a prototype. So what are the synergies between all of these programs? And it really comes down to the infrastructure that's required to fabricate these components and fabricate the fuel, and then the processes that are required to design and deploy them. So on the infrastructure side, part of that is centering around the fuel, which is in the middle of this slide. We're using fuel that's of a common isotope enrichment, so it's under 20% of the fissile isotope. So it's higher than what's used in the current commercial nuclear power applications, but it's going to allow for increased performance overall, while still mitigating some of the non-proliferation concerns. To be able to use these fuels, we need robust facilities, security, safety, and operational processes to be able to deploy them. And we also need specialty processes that are used to fabricate and coat the fuel kernel that can be common and leveraged throughout each of these applications, and then tailored for optimum performance and operation under the specific conditions of that application. And then on the process side, there's also, also on the infrastructure side, there's benefits not just to fabricating the fuels, but the reactors and all the components that are needed around, and the nuclear systems that are needed around the fuel. And this is infrastructure that's required both at BWXT and then across the government industrial base that's going to be needed to fabricate, test, and manufacture these systems. And then all of the associated specialty expertise around being able to safely produce high quality and reliable nuclear systems to apply across each of these use cases. And then last, there's the processes. So there's processes and capability that's needed to rapidly design, build, and test these new nuclear systems. This process and our approach to commercialization is one of the things that I love most about working at BWXT Advanced Technologies, because we're working to address the unique challenges that are associated with these applications and take these technologies from concept to reality. To do that, it takes a diverse team with a wide range of skill sets to be able to innovate through each of the stages of these projects and deploy new nuclear throughout a range of applications. And it's a really exciting team to be a part of. With that said, excited for the opportunity to talk about these projects, and I look forward to your questions.
Thanks a lot, Kate. This is a really exciting time, I find, across the government for nuclear systems, and you have an amazing plant there in Virginia. Next, we'll go to Joe. Why don't you talk to us?
Great, thanks, Jim. Can you hear me okay? Okay, great.
I muted too fast, yes.
Yeah, I just want to make sure I was unmuted. Thank you. So great, my name is Joe Anderson. I'm a Vice President of Business Development and Operations for Space Logistics, which Jim mentioned is a wholly owned subsidiary of Northrop Grumman. If we could go to the next slide, please. So Space Logistics was formed by Northrop Grumman specifically as the branding and marketing and contracting arm for all of our satellite servicing services and capabilities and products that we're offering. Currently, these products and service offerings include station keeping in orbit, so we can dock to satellites in orbit that are already existing in orbit. We're not designed for servicing. We can extend their lives. We can relocate these satellites around to different places in the orbit, perhaps take them out to the geograveyard orbit at the end of their lives. We can do inspections, we can do repairs, and we can augment them with new capabilities. So that's current offerings that we have today. The way we're doing that, our current objects in space, we have 2 MEVs. MEV is a mission extension vehicle. MEV-1 docked to its first client satellite about 1 year ago, just over 1 year ago. It docked to the Intelsat 901, which is the satellite you see in this image. This image was actually taken from MEV-1 as it was approaching the Intelsat 901 to dock with it last year, February. It's really the first commercial image of a satellite operating out in the geo environment. So really an exciting event there to take place. And then just recently, a few weeks ago, we docked with the MEV-2, docked with its first client satellite. The MEV-2 docked to the Intelsat 1002 spacecraft, which was operational at the time, delivering services to its customer, and actually never had an outage during the time that we docked with them. So that was fantastic. And I have a video coming up that will help illustrate how we performed that mission. And then, oh, no, don't slide to that slide yet, please go back. Thank you. And then looking forward, we have already started our next second generation product, which is our mission robotic vehicle. The primary mission of the mission robotic vehicle is installation of mission extension pods, which are small propulsion augmentation devices. So through these achievements, Northrop Grumman and their MEV team have really proven the value of on-orbit servicing, enabling commercial operators to be more competitive, expanding the realm of the possible for human and robotic exploration of our universe, and enabling previously unimagined resilience to our national security space. Now, next, I have a video coming up that illustrates how our mission extension vehicle rendezvous and docks to its client satellite. It has both some animation to help you see how it works, as well as embedded real images from the first docking of our MEV-1 to the Intelsat 901. So why don't you go ahead and go to the next slide. And we'll let that play.
This video starts with the MEV-1 already co-located with the IS-901 satellite in the geograveyard orbit, drifting westward across the Pacific Ocean. Soon you will see the MEV passing by the west side of the IS-901. You can see actual images from our infrared camera in the upper right. These images were taken from about 120 meters away as we circumnavigate to the first waypoint at which the MEV-1 stops and waits for ground command to approach. This waypoint is called the far hold and is about 80 meters behind the client satellite. Our ground controllers send the command for the MEV to proceed on to the next waypoint called the near hold, which is about 20 meters behind the IS-901. As the MEV-1 approaches the near hold, it slowly stops and once again waits for ground to provide permission to continue to the next waypoint, the capture box, which is about 1 meter behind the IS-901. Here you will start to make out the key docking interfaces that enable the MEV to capture and dock with the IS-901. These interfaces are the liquid apogee engine and the launch adapter ring, which are both conveniently located on the back of most geosatellites. The MEV uses a capture mechanism to extend from the MEV into the liquid apogee engine, expanding just beyond the throat to capture it. The capture mechanism is then retracted, pulling 3 stanchions up tight against the IS-901 launch adapter ring, securely clamping the 2 spacecraft together.
Unmute myself. So thank you. That was a really exciting mission. The first time docking had taken place in geo orbit. First time we've docked to a satellite that was not prepared to be docked with. So as mentioned, that satellite was launched back in 2001 that we docked with. So it never had envisioned that we would rendezvous and dock to that. But moving on to our next generation capability already, here in the image you see on the far left, our mission robotic vehicle. On the front face of that vehicle, you can see our robotic module has 2 robotic arms there that are provided through a partnership with DARPA that they call the RSGS, or Robotic Servicing of Geosynchronous Satellites. So these robotic arms, our primary mission for that is to install the mission extension pod that you see in the center there. That's a small propulsion augmentation device. It can provide 6 years of life extension to a typical client satellite. And you see in the picture here, the mission robotic vehicle preparing to install that mission extension pod onto the client. This mission robotic vehicle, of course, can be used for other things with its 2 robotic arms. It can grapple client vehicles to relocate them. It can do detailed robotic inspections and repairs. We can add other types of augmentation devices to our client satellites. So it's really beginning the first phases, in fact, of in-orbit assembly. So we're really excited about that. That system is planned to be launched in 2024. Okay, so we could go to the next slide, please. So just looking a little bit more ahead on our technology roadmap, we've already talked about today with our mission extension vehicle. We've talked about what we're launching in 2024 with our robotic vehicle and our mission extension pods. But our vision is that by 2025, every satellite will be launched that will include some form of servicing features. And in particular, one that we're working towards today is refueling and having prepared refueling interfaces. And so we're actively working on that today, as well as looking at feasibility of some active debris removal in the geo orbit using that mission robotic vehicle. And then looking a little further out towards the 2030s is when we really begin to utilize and make use of in-orbit assembly and manufacturing. There will be a lot, we believe, happening during this decade to prepare for that, but we think we really start getting the fruits of that capability in that time frame. And we're very excited about everything we're doing that's leading towards that capability. So Jim, thank you very much. I look forward to the discussion.
Thanks a lot, Joe. And that was, I want to extend my congratulations to you and your entire team for the MV2 recent success. That was just awesome to see, and really exciting fields. You're making great progress.
Great, thank you so much.
And, okay, Elliot, why don't you take us home for this part of the agenda?
Thanks, Jim, and I promise I will be quick so we stay on time. Good afternoon, everyone. My name is Elliot Carroll, and I'm the CEO of Lunar Resources. Lunar Resources, as Jim mentioned, is a space industrial company with an aim to industrialize the cislunar domain. We are developing space manufacturing and lunar mining technologies which have broad applications from low Earth orbit down to the lunar surface for space industrialization, exploration, and future colonization. Our 2 most prominent technologies are space deposition, which is the process of fabricating thin film materials such as solar cells and antennas in the vacuum of space and on the moon, as well as functional coatings such as optical coatings for remote sensing payloads and emissivity coatings for spacecraft. Space deposition is quickly becoming a critical technology across the OSAM segment of the space sector and one of the most enabling technologies for commercialization of space. Our second prominent technology is molten regular electrolysis, which involves a high temperature electrochemical process to extract and refine the lunar soil into raw commodities, including oxygen and constituent metals and alloys. This technology is unique as you only need metal oxide, which for lunar applications is the lunar soil, electricity and gravity. That is all. There's no need for reagents, no chemicals, just the lunar soil, electricity, and gravity. The technology is under rapid development with the target of operating a pilot plant on the moon by 2025. And if you can see in the background of our slides, you can see that that lunar resource extraction system in the far background, with a deposition rover manufacturing in situ solar cells on the lunar surface. And if you could go to the next slide, please. Thank you. And by developing these technologies amongst our other less known technologies, our goal is to enable in situ manufacturing, which is fabricating materials and manufacturing products in space from the materials off Earth to enable exploration and eventual colonization of space. And our current programs are focused on developing an in situ architecture for microgravity manufacturing of large space structures, servicing the space assets, and construction of lunar infrastructure. So with that said, Jim, I'll turn it back over to you.
Okay, great. Thanks so much, Elliot. That's a fascinating field. And I, one of the things that really excite me about the Artemis program and the CLIPS, the commercial lander services that we're working on is it enables opportunities to discover like this really promises. And so it's a great technology, and look forward to seeing that in operation. Okay, so now what we have is kind of, to me, a wow of the breadth of the types of technologies that we have, and I want to kind of see if we can pull on some common threads with you. And so I've got a question or two that I'd like to ask, and then we'll see if we have some questions from the chat. Hopefully we'll have some. But first of all, can each of you talk about your biggest challenge that you see in advancing the technologies in your field for enabling sustainable exploration? And we'll go Joe, then Elliot, then Kate, then Kerry.
Great, thanks, Jim. Thinking about this question, I think one of the biggest challenges that we face in satellite servicing area is the establishment of standards that will enable the industry to grow while not inhibiting innovation. We have, as an industry, we have formed a consortium called CONFERS for the rendezvous and servicing features. That it does include in-orbit assembly and manufacturing as well. So this consortium has published some principles and best practices for rendezvous and in-orbit servicing. We've already begun some stages of standards for those types of things through the ISO process. We have also delivered recommendations for RPO fiducials to AIAA standards making body. And we're now considering, what things should we do next in terms of standards? Looking at things such as, is it grappling interfaces or refueling interfaces or power and data connections, those types of things. But the real challenge here is, as a new industry, how do we do that? How do we do standards that will help the market grow while not inhibiting innovation? So it's one of the things that we're struggling with.
Okay, great. I remember when we were setting up CONFERS activities, and we, with the push towards let's let industry lead it, so that we can really get that. And of course, one of the biggest advocates of that is hopefully about to become our deputy administrator for NASA.
There you go.
So looking forward to it. All right, Elliot.
Yeah, thanks, Jim. And my answer is less tangible than Joe's, but for in situ manufacturing, our biggest challenge is just the general mentality in the space industry when it comes to space manufacturing and ISRU in general. And that's really because most recent space manufacturing programs have focused on very niche terrestrial products whom either the technology or the products market just hasn't materialized, as well as those products really haven't had a functional application in the space environment. And thus, space manufacturing has been highly discounted, at least in our experience. And regarding ISRU, the current focus within the US government has been just focused really on oxygen to refuel landers and spacecraft, and less focused on the metals, which effectively have been ignored, although 85% of the lunar soil by mass is made up of metals and other minerals outside of oxygen. So what we've been trying to do is encourage US leadership to take a new look at space manufacturing for functional space systems for space applications, as well as the utilization of metals from the moon for manufacturing those systems, whether that be for lunar infrastructure or making very large systems in space, particularly the structural elements that you need to make very large systems in space. And, over the next couple of years, our hope is that the U.S. space community gets to the point where when they are designing or developing new space systems, such as observatories or satellites, in the future, they ask, number one, just generally speaking, are there parts of these space systems that can be manufactured in space? And can these parts be fabricated with resources from space every time a new space asset is proposed? So that's our biggest challenge, and our, hopefully we'll get to that solution. And then, secondly, just funding for flight opportunities and payload funding for particularly lunar applications. And, we encourage Congress and members who are listening, or staffers who are listening to this call, that if they can, support STMD and NASA for more opportunities to do technology demonstrations on the lunar surface.
All right, thanks, Elliot. We never turned down a plug, but thanks. That was great. Kate, do you want to answer this?
Yeah. So I can certainly relate to the two challenges that Joe and Elliot said with regards to the nuclear industry. But I would say our biggest challenge is overcoming the cost and the timelines that are associated with deploying new nuclear technologies. And so with all of the programs that I mentioned, we're trying to push the limits of what's been demonstrated before. And to do that, we need to be able to continue to innovate on how we can design and test these technologies to reduce those timelines and consequently reduce the cost that's associated with them. We need to be able to gain confidence in our design and manufacturing processes. We need to optimize where and how fabrication development is performed to help us set us up better to scale up that technology that we've developed into a system that is a full-scale system and deployed in an application. I think on a positive note on some of these programs, I think there's examples of where that's being done and where we're trying to push towards a really rapid demonstration of the technology, even as early as in the mid-2020s.
Okay, yeah, thanks, Kate. Kerry?
Yeah, for us, we've been in development for a while and are ready to fly now. So I think one of the biggest areas for us is, if I compare it to Earth, on Earth, we rarely have trouble breathing, unless maybe we're climbing a mountain or exploring under seas. But in those situations, we have developed robust systems to help us breathe and stay at the proper temperature. But in space, we still have a ways to go. We don't have fully closed loop and regenerative systems. Some components and aspects of it are closed loop and regenerative, but as we go further and deeper into space, we need to bring all those resources with us and make the most of our ability to recycle the air and the water that's needed. So I think there's a lot of work to be done there. And I think one of the things that'll help us get there is actually more regular flights and more regular missions. And we DD-250 the Artemis 1 spacecraft to NASA earlier this year and are getting ready for that Artemis 1 mission and launch. And I think regular missions will help us get that flight experience we need and the knowledge to develop these closed loop systems that will sustain us on long duration deep space missions.
Yeah, thanks a lot, Kerry. It's kind of interesting that you're at different stages of development of some of these systems. There's operational, there's early stage, but if there's something that I would say was a theme is you're all dealing with transformative technologies in their own stages of development, and consistency in purpose and that which comes with funding as well as commitment is critical for advancing technologies. So this is great. I think what we'll do then is ask I have got one more question here, and then we'll go to the audience for a couple of questions. And so for each of you, would you talk about what you see as an overarching trend or a critical next step to significantly advance your technology field? Is it some trend or critical next step? And then we'll go Kate, then Kerry, then Elliot, then Joe.
All right. Thanks, Jim. To start, I would say, we really need to maintain the positive momentum that we've seen over the last several years in the government's appetite for new nuclear technologies specific to space exploration. But then second, we need to utilize advanced and emerging technologies to be able to reduce the costs that are associated with deploying nuclear technologies in space. These costs come in two phases. There's first the cost to develop. And so one way to address this would be to incorporate data technologies as a means to increase confidence in our models, use artificial intelligence to support design and manufacturing processes and more rapidly get through those phases, and use that to inform what we can design, what we build, and then what we test, and then ultimately deploy in a system. And then deployment costs are the second. So, incorporating how advances in manufacturing, and then using these government use cases for a high performance nuclear system to demonstrate that this technology can be transitioned into a commercial application.
Okay, thanks. Let's see, it was Kerry?
Yeah, I think that for sustainable long-term missions, we really need to build up the infrastructure and some of the aspects that each of the other panelists have been talking about and focusing on today. We need power, we need in-situ resource utilization, we need in-space manufacturing and assembly, we need communications. There's a lot of talk about 5G and implementing those kind of technologies on the moon. On Earth, it's easy to navigate because we have GPS satellites here. We don't have that at the moon. So things like that in the infrastructure will really break down the barriers to getting more people, more companies, more investors involved in a lunar economy. And the more people you get investing and interested, the more regularly you can fly. And I think that's when we'll see the tipping point of really a lot more activity at the moon. So I think we got to start with the infrastructure.
Thanks a lot. Elliot?
So my answer is more layman, but I'm very serious when I say this. For in-situ manufacturing, we need to go and do it. This technology has been developed for 20, 30 years, and we need to go to the moon and actually start doing it. So.
Well, that'd be a really good critical next step.
Absolutely.
Okay, Joe?
Yeah, so for us, we've already started our second generation of servicing system with the mission robotic vehicle and the mission extension pods. But we've also already begun working on that third generation system of, refueling prepared satellites, and that vision that by 2025, every new satellite launched is designed to be serviceable with refueling valves or power and data ports, items of that sort. But looking beyond that, even, it's really getting ourselves to that point of in-orbit assembly, in-orbit manufacturing that allow us to overcome many of the constraints we have today from the launch vehicle, and really expand what we can be doing in space at a much more affordable cost point.
Yeah, thanks, Joe, and thanks everyone for that interaction. I think I can really relate to all these. When we really love investing, I really love investing in transformational technologies and doing something in a manner with public-private partnerships that lead us towards advancing the field. And these are all great points. Okay, Jim, do you have some questions from the audience that we can?
I do have a couple. So the first one would be for Kate. You just talked a little bit about the commercial use for nuclear electric power. What's the biggest challenge there for allowing commercial entities to use nuclear electric power?
It's going to come down to approval, really, regardless of the domain. So being able to demonstrate confidence in the systems, I think that it's easier to overcome those for government applications because of the use case. it becomes more of a challenge once you get into a commercial space where there isn't as, it just becomes more of an uphill battle to demonstrate the safety of the system and demonstrate the benefit and demonstrate that there's an economic viability of being able to deploy it.
Yeah, and that was the second part of that question, was public perception of safety and risk, you know, overcoming all of that.
Yeah, that's, I think from an engineer's perspective, I'll give an example of, you know, the facility that Jim mentioned early on. And so that's the fabrication facility that we use to manufacture fuel and reactors. And there are, we have very robust infrastructures that are allowing us to be able to safely produce the materials that we need to. And I think a number of the other panelists are working in, you know, applications where there's a very low tolerance for failure and a low tolerance for, you know, issues going on in deployment. And I would say, you know, we're facing this, you know, they're addressing those concerns maybe more successfully than the nuclear industry is. But I would say there's use cases out there, and there's examples in other domains where, you know, they've been able to deploy, you know, high consequence systems.
And Jim, I'll just add a point too, because I always like looking for the places where we can combine government and industry together and try to get to a solution. So one of the things I think about this, I don't know what, this isn't saying we're going to do this or anything, but what I like to think about is if we could establish a basic capability in fission power that's government, you know, government purchase and a service to us for what our needs on the surface. Then what we could do potentially is have a public-private partnership where we would buy a base amount of power, and maybe the company, maybe we could work out some arrangement for, you know, that the company would be able to sell that other, the excess power or something like that. In that way, maybe we can enable a commercial market that would flow from a government and stuff and get around some of this overhead at first.
Excellent, thanks. So our next question is for Joe, but it might apply to others. It has to deal with the economics of it all. But this question was focused on debris removal. You know, so in essence, who's going to pay for that, and why should they?
Yeah, that's a big question. So certainly the technologies we're developing are, you know, directly applicable to debris removal. In one of the items on my chart there, we did mention we're looking at feasibility studies using our mission robotic vehicle that will be in geo orbit to, you know, potentially, you know, identify and capture debris that is a concern to a potential customer, right? And then take that debris away, maybe deposit it in the graveyard orbit out of the way. So we're looking at, and clearly all the rendezvous and docking capabilities we've developed here would be directly applicable to active debris removal in geo as well as other orbits. You know, active debris removal is not currently a focus market for our business because exactly what you said, there is currently no identified customer to pay for that. Clearly, we agree 100%. It is becoming more and more of a problem that the world will need to address. And you know, I think the technologies we're developing can be applied to it. But today, I do not see a paying customer stepping forward.
Anybody else have any additional thoughts on that? Well, I guess, you know, Elliot, talking to you, again, similar question. What about the economics of it? You know, you say go do it. Well, who's gonna? I mean, obviously, you know, NASA funded missions, things like that. But is anybody else interested in taking advantage of, you know, the electrolysis or the in situ resource utilization?
The answer is yes. So, you know, for the oxygen, obviously we have the Artemis program. And as part of that, you have a number of commercial companies developing lunar landers that need oxygen. And that market is, generally well understood in our industry. At least, the concept is well understood. You sell oxygen to people who need it for sending things back into space. But what's less understood is the market for manufacturing lunar infrastructure. Yes, that is, at least at first glance, for the government, but also building things back into orbit. So you extract the materials from the moon, and then you send it back into orbit for large structures. And there are, a number of advantages in doing so. Number one, depending on the size of your structure, and obviously these structures need to be very large, but our, technology is, the space industry technology is getting to a point to enable that the next big leap in capabilities will enable much larger systems. Is there's a huge reduction in mass that you need to launch from Earth. Effectively, the gravity well of the moon is thus that it makes economic sense to send things from the moon into geo orbit or cislunar orbit and have it tug. Number two, you have the ability to service these assets very quickly. And, I'm interested what Joe's thoughts were about servicing a satellite that from Lunar Resources per se. And third, you can scale these systems much bigger. And yes, obviously there's a DoD customer, but I think in the not too distant future, commercial companies such as Lockheed Martin and Northrop Grumman may be interested in making these much larger structures in space for commercial applications.
Excellent. Thanks, Elliot. There was something else about regulatory concerns, about setting up, colonization or setting up stations on the moon or on Mars or even, in orbit. Is there any sort of regulation that's being talked about towards sustainability, meaning regulation toward not producing unremovable waste or like we just talked about, debris, things like that, that might be coming together on a national or on an international basis?
Well, I'll start. I think given that question, what I would say is, of course, we've been working on the Artemis Accords. And really very successfully. There's an awful lot of, there's several, a number of companies that are now countries signed up to it. And the idea behind that is let's enforce and reinforce the Outer Space Treaty, which says that basically that we can go to the moon and take possession of something without it violating an overall or staking claims to the area as a whole, and without it violating an outer space treaty. And so with that, then we can open up the possibility that we can have a commercial entity that would go through and potentially be able to operate in that environment. And in fact, you saw that when NASA put out the challenge, it has put out the challenge to try to take possession in place, and that was really solely to have a case validation. And what I'll say otherwise too is touching on this the idea is, well, who's going to pay for this? It's really key to our understanding of sustainable exploration. Part of what we want to do for sustainable exploration is build from this to grow to the Mars and on, but also part of it is to enable an industry so that NASA can start as being the primary tenant, the primary customer, but what we really want to evolve towards, we're not the only one and stuff. And if we can get to that, so that is a key to us, is understanding how much we have to have as an investment in the basic utilities and capabilities to enable some other entities to start paying.
Yeah, I guess I'll add on to that, because we're really looking at what is that lunar economy and what's the commodity, what's the currency of exchange there? Is it water? Is it Elliot's company mining that and then other companies buying it for crew sustainment or to use as to create fuel? or is it helium-3 or any of the other resources that are on the moon? We need to, I think that the government and NASA can help set up that infrastructure that will allow other companies to take that to the next step of, okay, we've identified the resources and the commodities that we want to do the next step in the human exploration and colonization of these faraway places.
Okay, Jim, do you have a question? I have another question I can ask.
You go ahead, Jim.
Okay, so each of the panel members, could you, I think this fits with what we've been talking about, but share possible avenues for government to incentivize industry to advance the needed technologies in your field and advance, make an economic case for it. And we'll start with Elliot, then Joe, then Kerry, then Kate.
So, Jim, at Lunar Resources, we've been playing with this new concept. It is a little bit non-traditional, but nonetheless, it is an idea to create a federal carbon credit program for any product produced in space from space resources. So obviously on the moon, we know that there's essentially no usable carbon, but for anything produced from the lunar soil, or really any space resource for that matter, it eliminates that carbon footprint for that product produced on Earth. So for example, Lunar Resources has a phase 1 NIAC to look at making an observatory on the far side of the moon that involves over 100,000 dipoles. That's a lot of metal, that's a lot of fabrication. So the concept is when we extract and refine materials from the moon and then manufacture those materials into products and thus industrialize space, we can be issued a carbon credit which can be sold in the carbon marketplace to incentivize the industrialization of space.
Okay, that's pretty interesting. We use a place where there's no carbon to help us get to zero net carbon on Earth. Joe, do you want to comment?
Very creative, very creative. Well, my response here is that governments can really help make the market by buying sustaining services from commercial service providers like space logistics. Start requiring that government in-space assets should use satellite servicing to utilize them as long as they can, continue to deliver their useful services or data, either through repairing those items in space or cost-effective life extensions. For example, as NASA STMD pushes to save more money on small disposable science missions, they should also be using their senior review to see what missions could be economically served with a robotic repair or a life extension. Another important avenue for governments to incentivize industry, I think, is by simplifying and reducing the costs, the burdens, and the time required to transfer technology to the private industry. So I think there's a lot of good things that NASA has developed and other government agencies have developed that, if that process were simplified, the commercial market could do a better job of utilizing those and making more from it.
Yeah, thanks, Joe. Kerry?
I think there are some things the government is already doing that are helping incentivize industry. Things like the programs the Space and Technology Mission Directorate is doing, like tipping points, and some of the recent awards there in helping develop these breakthrough technologies. Lockheed Martin was recently awarded a contract to work on a cryogenic demonstration mission where we're practicing cryo fluid management, in-space fuel transfer, and things that will help us get to the next breakthrough technologies with these public-private partnerships where there's industry investment as well as government investment in key technology areas.
Yeah, thanks. We've really appreciated that program's great, and we've gotten lots out of it. So congratulations on that. And Kate?
Yeah, I think this goes back to what I said earlier about maintaining all the momentum that's behind nuclear development at this point. So we need to continue to advance that use case for, government nuclear applications, whether that's propulsion, in-space surface power, that can lead to choosing a initial demonstration mission, and then something that can be the jumping off point for a longer duration or a higher performance mission that requires nuclear as the solution. And then use that development to deploy those programs and reduce the risk that exists, whether it's for commercial applications or beyond the lunar surface. So, and then to do that, you need to create and foster more synergies and keep the ones that you currently have with the technologies that are being deployed. So fuel was an example of that. The auxiliary equipment around the reactor and around the fuel is another example. And just continuing to collaborate on those areas to best utilize the government resources and investment.
Okay, thanks a lot, Kate. Jim, I think you have another question, and maybe I know we're running low on time, so maybe that'll be our last question from the audience, and we'll wrap up. If that's
sure. So yeah, this one is for let's see, Elliot and Kate. And the question comes from our audience, and it's, how do you simulate conditions, moon or Mars or space, to ensure that your technologies will work when you get there? So, Kate.
Yeah, so it really comes down to data. And so the more data that we have on systems, either existing systems or extrapolating to what we would envision the conditions being for those specific applications, the better our tools get at simulating and modeling, what's going to occur. Getting as much test data as we can in the most economic way possible is another avenue by which we do that. And then really it takes a really smart engineers doing things that I don't fully understand the ins and outs of to get into the details of what it's going to take to with confidence model these complex systems.
Great, thanks. Elliot?
Yeah, not sure I have much more to add than Kate, but with our different technologies, which we have multiple of them, and each are very different. So some are manufacturing based and some are resource extraction based. So some of them, are affected by gravity, such as lunar gravity. Some it's completely irrelevant for gravity, such as our deposition technology. So we do our best to, of course, develop the systems for the environment they're gonna operate in, and then do as much modeling, whether that's using COMSOL or SolidWorks and so forth, and then send them into the vacuum chambers, send them into the, we're working with the folks, we're simulating lunar G on space flight opportunities for the suborbital folks. So just test it as close as you can to a lunar, relevant lunar environment is kind of our protocol.
Gotcha. Great. Jim, I'll turn it over to you for any closing remarks.
Okay, great. In lieu of closing remarks, or I'll have one, but I'm going to cheat a little bit. I'm going to ask you for a lightning round question for each of you. And so it's 4 words or less. And what excites you most about the job that you do? And Kate, you already answered this once, but it's got to be something different. So we'll go back to the original order, Kerry, then Kate, then Joe, then Elliot, real fast.
Words or less, that's a challenge, but I'm going to say the people and the missions.
Great.
I've now had my original and my backup. I would say the opportunity to push limits.
Great. Joe?
So was I next? All right, so I'd say
yeah,
entrepreneurship within established company.
That's good. Elliot?
The industrialization of space.
Awesome. All right, Jim, this was a pleasure, as always, to work with you in this. And thanks so much for the panelists for your great insight. And I really appreciate the audience for your participation. So thanks much.
Yeah, thank you so much to everybody. Really appreciate everybody jumping in here and doing this. It was a great conversation. It was fantastic. So thank you so much. Thank you, Jim.
Bye. Yeah.
All righty.
Thank you.
Okay, so that's it. Thank you to all of our speakers and panelists for such a great day. We really appreciate everybody's participation. Thank you to our event sponsors. Aerojet Rocketdyne, the Aerospace Corporation, Ball Aerospace, Blue Origin, Johns Hopkins Applied Physics Laboratory, KBR, L3 Harris, our education sponsor, Lockheed Martin, Northrop Grumman, SAIC, Teledyne Brown Engineering, and our media sponsor, Space News. Thank you to everyone at the NASA Goddard Space Flight Center for all your contributions and collaboration. And we will see you all tomorrow morning at 11 a.m. Eastern for another great day of the Goddard Symposium, including presentation of some special awards, as well as our keynote speaker, Ellen Stofan. So thank you very much again. Have a great evening.